Hi, I'm Po-Shen Loh. I've been thinking about how to explain math in more thoughtful and interesting ways. A few months ago, I was thinking about quadratic equations, and I was really surprised to find out that you can solve them in this really simple way. I couldn't believe that I'd never seen this before in any textbook. So I'm sharing a detailed explanation of the method here with examples. First, I'll show the method for a few seconds. Just jump back here in the video and pause whenever you want to see it again. The words are carefully chosen so that the method is logically sound. Let's get started. This technique actually doesn't require much more background knowledge than what's called the distributive property. To review that, suppose I have x minus 3 multiplied by x minus 4. How do you expand these brackets? Just remember, you find all the ways of taking something from each of the brackets and multiplying together. When I do that, if I take the x and the x, I get x squared. If I have the x and the minus 4, I have minus 4x. If I take the minus 3 and the x, I have minus 3x. And if I take the minus 3 and the minus 4, they multiply to 12. And usually we simplify this expression by putting together the terms that are similar, meaning they have the same number of x's multiplied together in them. So we can often write this as x squared minus 7x plus 12. Before we go on, I just want to look at this and notice a pattern. Where does this minus 7 come from? That actually comes from the minus 3 plus the minus 4. I could also say, where does the 7 come from? It comes from the 3 plus the 4 if both of those have negative signs. How about the 12? It's the negative 3 times the negative 4. Also, if I was going to write down two numbers after negative signs, their product would be that 12, because the two minus signs would multiply to make a plus. Let's review one more. Suppose I want to expand out a different bracket. What if I have something like 3 minus u times 3 plus u? Here I just want to emphasize there's nothing magic about x. Algebra lets you use any letter that you want to use. If I expand this out, all the possible ways of combining pairs, if I take the 3 and the 3, I get 9. Then the first 3 and the last u gives me plus 3u. The first minus u and the second 3 gives me minus 3u. And the last term is minus u times plus u, which is minus u squared. So here, if I want to simplify, I could actually cancel the 3u minus 3u, and I'd get 9 minus u squared. Actually, that's kind of cute. There's not as much as in this one. This expression has more stuff in the middle. And that's because these two middle terms cancel. And that's actually because of the form of what I have here. Because this 3 went with that u, and this negative u went with that 3. That's kind of neat. And in math, we actually love to see these kinds of cute coincidences. They can sometimes come in handy later. Okay, so this was a review. But why would anyone actually care about this? Well, first of all, it's useful to be able to expand brackets. But second of all, it turns out that this is an interesting way of solving quadratic equations. Let me write down this top piece again in a slightly different order. You see, I now know that I have another way to write x squared minus 7x plus 12. It's like that. So x squared minus 7x plus 12 is also x minus 3 times x minus 4. Now, when we talk about a quadratic equation, oftentimes what's called a standard form quadratic equation is something like this thing on the left equals 0. You want to know when this thing is 0. But there's something nice that happens. If you can write this as a product of two things, if I want to know exactly when is this whole thing 0, I can just ask exactly when is this whole thing 0. This is a product of two numbers. If I have an x is a number. If you plug x in, you'll get a number times another number. If you multiply two numbers together and get 0, that happens exactly when one or both of the numbers is 0. That's actually called the zero product property. And so if I know that this quadratic can be rewritten in this way, that means that the quadratic is 0 precisely when either this is 0 or that is 0. It's a precisely when. So then, when is x minus 3 equal to 0? X minus 3 is 0 exactly when x equals 3. On the other hand, x minus 4 equals 0 precisely when x equals 4. So what this tells me is that the two solutions to this quadratic equation, this equals 0, are exactly x equals 3 and x equals 4. Those are the only values of x which, if I put into here, spit out 0. And also because if I need this to be 0, the only way I can multiply two numbers to get 0 is if one of them is 0. I spent a lot of time talking about this because the logic is actually quite important. But the conclusion here is that if I'm trying to solve a quadratic equation, if only I could find this magical factoring, then I can read off the answers. The answers are whatever make this 0 or that 0. In this case, it's the 3 and the 4. What I've talked about so far is actually not a new technique. It's just called the method of factoring for solving quadratic equations. The method of factoring is to try to take your quadratic and write it as a product like this. Let's try using this factoring to solve a question. X squared minus 14x plus 24 equals 0. Now, if we want to do this by factoring, we would like to try to write x squared minus 14x plus 24. We would like to write it as x minus something times x minus something else. Sometimes in books, you'll see plus signs instead of minus signs here. I'm using minus signs on purpose because that's going to let us learn something deeper in math as we keep going. And it's also going to be more convenient. So I would really like to find two numbers to put there. Just as we saw before, if I find these two numbers, then those two would actually be the solutions of this quadratic equation. And what do these two numbers need? If you think about what happens as you expand the brackets, I would need to find these two numbers so that they add to 14 and they multiply to 24. I didn't say add to minus 14. They have to add to positive 14 because I already have minus signs here. I'm talking about what do I write in these pinkish purple blanks. I want to write two numbers there that add to positive 14 and multiply to positive 24. And I'll write that down like this. If I can find two numbers with a sum equals to 14 and a product equals to 24, then those two numbers are going to be the solutions of this quadratic equation. And not only the solutions, they are all the solutions to the quadratic equation. So the game then becomes to find these two numbers with this sum and this product. Notice there's a big word if here though, because I don't actually know that these two numbers exist. And the way that people usually go about finding these is actually with a method called guess and check. That's what I learned as well when I was going to school. But it turns out there's a much, much easier way, and this was the thing that surprised me, and I wanted to share with everybody else. You see, we're used to thinking of this as a factoring method, so we always try to factor the product. And we're thinking about all these different ways to prime factorize 24, and then find ways to take two factors of 24 that multiply together to make 24 and add to 14. The trick is actually to start from the sum. I need to find two numbers with a sum of 14 and a product of 24. Two numbers have a sum of 14 exactly when their average is 7. And two numbers have an average of 7 exactly when those two numbers are 7 minus a little bit and 7 plus the same bit. So what I'll write here is an arrow, and I'll say, I just need to find a u. So that 7 minus u and 7 plus u give the product. Because if I found a u so that 7 minus u and 7 plus u gave that product, they would already give the sum. They're already set up so that it's the average minus a bit and the average plus the same bit. Why did I call this u? I want to use u for unknown, I guess. So now I just need to find this u so that this happens. But this is where the beautiful thing happens. What is the product of 7 minus u and 7 plus u? That's actually the beautiful form that we saw at the outset of this video. If you multiply this together, you would actually get 49 minus u squared, because the middle terms are going to cancel. That's the product of 7 minus u and 7 plus u. I need that gives me the product of 24. All of this in yellow is actually equivalent. Finding a u so that 7 minus u times 7 plus u gives the product is exactly the same sentence as saying that 49 minus u squared equals 24, because that's just the product of those, and the 24 is the product that we seek. Can we find a u so that this is true? If you do a little bit of arithmetic, if I found a u squared that was 49 minus 24, that would work. So actually, I'm okay if I find a u squared which is 49 minus 24, which is 25. I'm going to draw an arrow up. And what that means is if I have a u squared which is 25, then I have that. Do you see a u which squares to 25? Yes, 5. So I can actually say u equals 5 gives me that u squared equals 25, and so on. I'm going to emphasize that this exists. That means a choice of u exists to make all of these happen, which means that I can get two numbers with a sum of 14 and a product of 24. Just put 5 into there. If you put 5 into there, what do you actually get? You get 7 minus 5, which is 2, and 7 plus 5, which is 12. And you can check that those two numbers do add to 14 and multiply to 24. But even if you didn't check, we would know it had to work because all of these arrows flow upwards. That's how the mathematical logic is working here. You might be wondering, why didn't I write plus or minus 5? It's because I actually don't need the other direction in order to finish. I just need to know there's a flow from here up. By the way, there's also a flow if I chose to write a minus sign here instead. If I said u equals minus 5, that also gives me that u squared is 25, and I can keep going. And what I would get from this is I would get that 7 minus negative 5, which is 12, and 7 plus negative 5, which is 2, are two numbers that work. Those are the same pair. So that's just showing that whether you wrote the plus or the minus, it actually wouldn't make a difference. But because I found out that these two numbers exist, the if is done. And so I get the then, and they're all the solutions. And this is a technique that lets you do this without any guessing. You might say, it seems like I took forever to explain this technique. That's because this one time I explained it, I wanted to make sure that the flow of logic was 100% clear. Okay, let's try some other equations. X squared minus 8x plus 13 equals to 0. If you're familiar with the factoring method, you'll actually recognize this as something that can't be factored normally, because 13 is a prime number. But let's try writing down what we'd like to do with factoring. We'd like to be able to write down a factorization. X squared minus 8x plus 13 equals x minus something times x minus something else. These are two blanks. And just as before, what this means is if we can find two numbers with sum equals to 8 and product equals to 13, then they are all the solutions. And again, this is a positive 8 because I'm putting numbers into these blanks that are after minus signs. Okay, and as we can see, we have a lot of trouble finding numbers that multiply to 13 because 13 is a prime. If I try 1 and 13, 1 times 13 works, but 1 plus 13 is not 8. But if we start from the sum instead, it's great. What would give me a sum of 8? Well, an average of 4 would give me a sum of 8. That means that I need to find a u, so that 4 minus u and 4 plus u give the product, because they're already going to give the sum when I add them together. And if I multiply these two together, it's again going to have the middle terms canceling. That's exactly the same thing as 16 minus u squared being equal to 13. Maybe you can see what you should choose. In order to get 16 minus u squared to be 13, I'll be in good shape if u squared is 3. That's 16 minus 13. And for that, I'll be in good shape if I choose u to be positive square root of 3. If I chose u to be negative square root of 3, that would also work. Pulling all the way back up here, this tells me that if I use 4 minus the square root of 3 and 4 plus the square root of 3, these are two numbers that would give a sum of 8 and a product of 13. This is where it's really convenient not to have to actually multiply them together to finish up. We're simply using the fact that the logic is flowing upwards. If I used u to be root 3, then u squared is 3, then 16 minus u squared is 13, then I have the product, and I'm good. Sometimes we write this in a little bit more compact way. Another way to write the answer is 4 plus or minus the square root of 3. And that's because it has both the minus and the plus inside it. There's actually something quite interesting about this solution here, because these answers are not integers, so it would actually be very, very difficult to guess them. But this shows that this technique actually can solve any quadratic equation, even when the solutions aren't integers or rational numbers that you can easily guess. And in fact, this works for all kinds of quadratic equations. Let's now do a bunch of other ones that just show how general this technique is. X squared minus 8x plus 18 equals to 0. By now, hopefully it's familiar what we're doing. So I'm just going to say if can find two numbers with sum equals 8 and product, I'll write PROD, product equals 18, then they are all the solutions. Okay, let's go faster. To get a sum of 8, all I would need to use is two numbers which are equal distance from the average. So I would just need a u so that 4 minus u and 4 plus u, they give the product of 18. And if I expand what happens when I multiply those together, that's the same as saying 16 minus u squared is equal to 18. In order to get that, I could achieve that by having u squared equal to 16 minus 18. In this case, it's negative 2. Can you have a number squared to be a negative number? You can if you allow imaginary numbers, complex numbers. And I will say that's actually one of these reasons why complex numbers are so useful. The fact that we can go ahead and say there is a choice of u that makes this true allows this technique to work, but also allows you to solve quadratic equations in general. You might be wondering, is it okay to just go and add a number like this that doesn't seem to exist? In ancient times, people had the same misgivings, the same worries about negative numbers, like negative 3. If you ask somebody, what is negative 3? They might say, I'm not sure. If you can show me negative 3 sheep, I'll believe you. But these days, we seem to understand that negative numbers are useful for doing calculations because it's useful to be able to have your answer become negative and then add some stuff and have it be positive again. The same thing is happening here. I can get u squared to be minus 2 by choosing u to be the square root of minus 2, and the square root of minus 2 is the imaginary number I times the square root of 2. I is the square root of minus 1. By choosing this particular u, then its square is minus 2, and I can keep going, and it works. And if you put a minus sign in front, that would also be okay, but we don't need that here. And so going back up here, we now find out that two numbers that sum to 8 and multiply to 18 are 4 plus or minus I times the square root of 2. And so this technique even works when the solutions are imaginary. When you see this, you actually realize that you don't need the quadratic formula even. This technique can be used to solve any equation. Although you might be saying, these numbers here, it seems like we always had the signs, the pluses and minus signs in the right place. Well, let's try something else. What if I switch up the signs a little? X squared plus 6x minus 4 equals to 0. Just to review what we're looking for, we want to factorize this as x squared plus 6x minus 4 equals x minus something times x minus something. We're hoping that we can find this kind of factorization. At this point, I should also say, it's kind of miraculous. We always seem to be able to find this factorization. And that's because we were able to take square roots of negative numbers. That's why complex numbers were useful. And you might wonder, why do we want to try to factor into multiplying 2 of these? Well, if you tried to factor with multiplying 3 things like this, you'd actually have an x cubed term. It just wouldn't work. Okay, so now, in order for this factorization to exist, what do I need? I'll write my whole thing again. If can find two numbers with sum equals, this time, the sum is going to be minus 6. And that's because I'm insisting on putting these minus signs here. Putting minus signs here is what lets me eventually say that the numbers in these blanks are the exact solutions to this quadratic equation to begin with. Because if you remember, we used the fact that multiplying two things to get 0 happens precisely when at least one of them is 0, and x minus blank is 0 precisely when x equals blank. So I need two numbers with sum equals negative 6, product. This time the product has to be minus 4. Minus this blank times minus that blank is just the product of those two blanks, and that's supposed to be minus 4. Then they are all the solutions. Okay, so I just need u so that half of minus 6, which is minus 3, minus u, and minus 3 plus u give the product that I want. If I try multiplying these, again the beautiful thing happens. Actually, this beautiful thing is called a difference of squares, because that's exactly what we're doing. The difference of squares is 9 minus u squared being negative 4. Now, how could I get that to happen? I can make that happen when u squared equals 9 minus negative 4, which is 13. And so I could make that happen by choosing u to be square root of 13. Again, choosing minus square root of 13 is also okay. If I put it up here, then I find that my two solutions are minus 3 plus or minus the square root of 13. And it works again. So even if these signs are not the exact beautiful pattern, it's okay. Just think about how this factorization works and just follow your nose, and you'll figure out what the sum and product would need to be in order for the factorization to exist. And again, every time since at the bottom I get a u that exists, that works, I'm able to go all the way to the top, get my if to be true, and then they are all the solutions. Okay. So far, we've still been lucky, though. We're always dividing this second number by 2. We're always taking this sum and turning it into an average. What if it's odd? Let's try another one. x squared minus x minus 1 equals 0. Actually, the same thing works. If can find two numbers with sum equals to 1 and product equals to negative 1, then they are all the solutions. Okay, how would I get sum equals to 1? Then I could do that by having average equals to half. So I need to find a u so that 1/2 minus u and 1/2 plus u give the product. That is precisely equivalent to, when I take the difference of squares, 1/4 minus u squared being equal to negative 1. How to get that? I could get that by having u squared equals 1/4 minus negative 1. It's 1/4 plus 1. That's 5/4. And so I could do this by having a u, which is the square root of 5/4. I'm going to write it like this: root 5 over root 4. And that's because root 4 is 2. So that means that my solutions here are 1/2 plus or minus root 5 divided by 2. Actually, oftentimes people will collect it over a common denominator and write 1 plus or minus the root 5 all over 2. And again, since I got u to exist, all of this logic flows. I'm able to get two numbers with a sum of 1 and a product of minus 1. Bam! And those are the solutions. Actually, this is a fun equation. If you like math, one of these solutions is what's called the golden ratio, which is the ratio of the length to the width of the most beautiful rectangle in the world. Let's do one more complicated equation, just to see what happens if the front is not just x squared. What if I have something like 2x squared minus 4x minus 5 equals 0? Oh no, then everything breaks, right? Well, not really. Actually, the beautiful thing about algebra is that you can do anything you want to both sides of an equation to try to make it into something you'd rather deal with. And we'd rather deal with stuff which has just an x squared without anything in front of it, 1x squared. So just divide everything by 2. This equation here is equivalent to, equivalent means it has exactly the same solutions to, because I just scaled everything by 2, x squared minus 2x minus 5 over 2 equals 0. Every solution of this is a solution of that, and vice versa. Because to go from this equation to that one, I could multiply both sides by 2. And to go from this one back down, I could divide both sides by 2. Both are legitimate things to do to both sides of an equation. Okay, so now if I have this, we just move back into the framework we've had before. If can find two numbers with sum equals to 2 and product equals to minus 5 over 2, then they are all the solutions. Following what we've done before, we just need u so that 1 minus u and 1 plus u give the product. And that's the same thing as 1 minus u squared being negative 5/2. Okay, how to get that? Just as before, I could get that by having a u squared, which is 1 minus negative 5/2, which is 7/2. And we're just using fractions. Actually, there's nothing special about this. It just means that we have to deal with fractions instead. This happens when I choose a u, which is the square root of 7 over 2. I'm going to write like this, root 7 over root 2. So the solutions to this are just 1 plus or minus square root 7 over square root 2. I will say that sometimes people prefer to write this in a little bit more pretty way, where you don't have a square root in the denominator. That's called rationalizing the denominator. And if you multiply the top and the bottom of this fraction by root 2, that's the same as 1 plus or minus root 14 over 2. Both of these are actually the correct answer. It just depends on whether you're supposed to give your answer in a form that has no square roots in the denominator. At this point, we've seen that actually this technique can solve every quadratic equation, because this technique will always come down to just take a square root at the end. And that actually lets you derive the quadratic formula if you want. Let's do it this way. Let's start by deriving the formula for something like x squared plus bx plus c equals 0. If you can find two numbers with sum equals minus b and product equals c. That's actually what we have to do here. Then they are all the solutions. So just as before, in order to get a sum of minus b, I just need to have an average of minus b over 2 to get that. So I need a u so that minus b over 2 minus u and minus b over 2 plus u give the product, which is exactly the same as b squared over 4 minus u squared equals c. How can I make this happen? I could make this happen by having u squared equal to b squared over 4 minus c. And the way I could make that happen is by having u equal to the square root of b squared over 4 minus c. Again, if I chose negative square root, that's also okay. That would give me a solution set too, but it would be the same solution set. And the very important thing is that this actually always exists. Because no matter what b and c are, I can always take the square root of any number. I might just get an imaginary number. Putting it all the way back up here, I find that my solutions to the quadratic are minus b over 2 plus or minus the square root of b squared over 4 minus c. That might not look like the quadratic formula that you're used to. It's actually equivalent to it. But if I really wanted to get the quadratic formula that you're used to learning, we'd want to do that with something in front of the x squared as well. So for the grand finale, let's now do it with ax squared plus bx plus c, and we're actually going to use this formula here as a shortcut. If I have ax squared plus bx plus c equals to 0, just as before, all we have to do is divide by the a to get an equivalent equation. Here I'm confident saying divide by the a, because if a was 0, then it wouldn't be a quadratic equation anyway, and you'd have an easier way to solve it. So I'll have x squared plus b divided by a, x, plus c divided by a equals 0. And these two have the same solutions for x, because from this equation I can times a to get that one, and for that equation I could divide by a to get this one, because I'm saying a is not 0 in everything I'm doing. Now, to get the solutions of this, you could actually do the same thing we had done with this sum and product. But the shortcut is to say this is already in the same form as what we have found a formula for. You see, it already is x squared plus something x plus c. So I can just use the previous form, where I actually will put that b is equal to b over a, little b over a, and the capital C in the other form is the little c over a. I know I have big and little letters, so I'm trying to emphasize that's a capital C and that's a lowercase c. But if I use these two, that is x squared plus capital Bx plus capital C equals to 0. And so from what I did before, I know that the solutions are, it was negative capital B over 2, which is negative b over 2a, plus or minus the square root of capital B squared over 4. If I do that, I will get little b squared over 4a squared. And I needed to minus the capital C. So that's minus the c over a. This is the quadratic formula, right? Again, it might not look like what you're used to. To be honest, if you plugged in a's, b's, and c's, you would get the same answers. But let's clean this up and you'll get something that you're used to seeing. The easiest way to clean this up is to write that the beginning is still minus b over 2a. But the next term, what we'll do is we'll put everything over a common denominator, 4a squared. That leaves b squared here. And when I say a common denominator, if I want this to be over 4a squared, then that would be a 4ac over 4a squared. So that's 4ac. Okay. If I want to continue simplifying, I can use the fact that the denominator 4a squared is exactly the square of 2a. So I could also write that this is minus b all over 2a plus or minus the square root of b squared minus 4ac all over 2a. There is a little technicality here in that I said I could write, instead of the square root of 4a squared, write just plain 2a. Actually, you don't know whether it's the plus or the minus square root, but the thing is it doesn't matter because in front I'll have a plus or minus sign anyway. Finally, I can make this look a lot more elegant by combining everything over a common denominator of 2a. And so that is just negative b plus or minus the square root of b squared minus 4ac all over 2a. That is the quadratic formula that everybody learns. Although we got to the quadratic formula at the end of this video, I want to emphasize that the goal of this video wasn't just to derive the quadratic formula so that we can now memorize it. Rather, it's better to see that some parts that used to be done by guesswork have been replaced by a clever trick. And also, you can now use that to reason through every single step of solving a quadratic equation, even if you forgot the quadratic formula. Here's all you do. You start with any equation. If it doesn't look like this, just divide by what you need to make it have nothing in front of the x squared, meaning it's just 1x squared. And then the key is, because of factoring, if you can find two numbers who have a sum and a product that correspond to these coefficients, these numbers in front of the x and this constant, this thing with no x's, if you can find those two numbers, then those two are all the solutions. I want to actually, at this point, say these ideas aren't actually new. This particular relationship between the sum and the product of the two solutions of an equation and the coefficients is actually often called Viète's relations. And that was known hundreds of years ago. Viète was a Renaissance-era mathematician. So in fact, what we've just done here is we have also proved Viète's relations for quadratics, for things which are with x squared as the highest power of x. So there is a relationship here between Viète's relations and this method. This method establishes Viète's relations. But I should say this technique has been known for hundreds of years. This trick, I also want to emphasize, this particular trick is also not new. The trick of saying, if I have to find two numbers with a given sum and a product, that was actually done thousands of years ago by the Babylonians. The Babylonians knew that if you wanted to solve these problems, the easiest way would be to go from the average plus or minus a certain amount. So this particular technique is actually just the combination of two tricks or insights that have been known for hundreds of years and thousands of years. That's what makes it all the more surprising that this method hasn't been the one that we all learned in school. Hopefully, by combining these insights from the ancient mathematicians, all of our future generations will not have to do any more guessing.